Here, what we're going to do next is we're going to try to find the potential difference between 2 points. So in that case, let's write that down. Between 2 points. So let me draw the circuit. So let's consider that I have the circuit as so. Where again, I have a battery. And then I have the resistor that is connected again in series, right? So this battery is essentially part of a battery that is a real EMF device, meaning it has an internal resistance. So in that case, I will have a resistor in the battery, and the battery has a positive terminal which will be on this end, negative terminal on this end. So it will obviously have an EMF induced, and it will be in the direction of the current, right? And the internal resistance will be denoted as small r, and the external resistance in the circuit will be denoted as capital R. And let's denote 2 points. Let's say I have point B over here and I have point A over here, which are the 2 points that we're going to consider to find the potential difference from, right? And the current has a direction in this direction, which is the conventional direction of current, which flows through the circuit in this way. So now we're going to find the potential at point B from point A. Okay, so in that case, basically just for this part, as I move from A to B, what will be the potential difference? So if I start at A, I know that the potential at that point, let me denote that as VA. Now I'm moving through, and the first component that I encounter is the battery. So in that case, it will add to the potential of the circuit, so therefore a plus zeta, right? And then the next component that I encounter is the internal resistor, so therefore it will take away from the potential, and this will be minus I small r, and this would be equal to the potential at this point, VB, right? Which is because this is where I'm stopping. So if I rearrange this a little bit, VA, or let me read, VB minus VA will equal to zeta minus I R. Okay, now if I want to evaluate the current for this, just rearranging, I know current for an internal where an internal resistance exists is given as zeta by R plus R, right? This is what we found out earlier. So in that case, I can plug that in over here, and what I would get is the following expression. So I have VB minus VA, which equals to zeta minus, so for the I part, I would get zeta by R plus R, and this is times small r, right, as per this expression over here. And therefore, rearranging this a little bit, I would get VB minus VA to be equal to zeta by R plus R, and this time times capital R, just doing the LCM. And this is essentially your potential difference between 2 points, B and A. So now let's put in some values. Let's consider that we are working with the fact that we have R equals to 2 ohms, capital R equals to 4 ohms, and the EMF equals to 12 volts. In that case, what would be the potential difference between VB and VA, right? Basically, what would be this numerical value, right? So in that case, let me just plug everything that I have over here. In that case, VB minus VA, considering the values over here, I will get EMF as 12, capital R as 4, small r as 2, and this multiplied with capital R, which is again 4. So in that case, I get 8 volts. Okay, now remember that I went from A to B in this direction, right, which was the clockwise direction, but I can do the same because, as you remember, the direction of the loop doesn't matter, right? So in that case, I can go counterclockwise as well. In that case, if I did go counterclockwise, that means in this direction, then I would have I would start out with VA, and then I would encounter this component first, which is the resistor, and since this is in the opposite direction of the current, therefore যেখানে আমার মাইনাস হওয়ার কথা এখন এটা প্লাস হবে, so therefore I will get my plus I capital R, and then I would reach B point over here, which is VB, right? So in that case, rearranging it, VB minus VA becomes IR. And similar to what I did earlier, and I know I equals to this expression over here, so if I just plug that in, I would get zeta R plus small r times R, which is exactly the expression that I have over here, which sort of proves that it doesn't matter which direction you take, the loop can be in either direction, counterclockwise or clockwise, it will still give you the same result. Now I can make a statement over here and write that to find the potential between any 2 points, in a circuit, start at one point and traverse the circuit to the other point. Following any path, because the loop direction does not matter, following any path, and add algebraically the changes in potential you encounter. So যত components আমরা encounter করতে থাকবো ওগুলো just incorporate করতে থাকবো. Okay. Now furthermore, there's a couple of definitions that I want to include, like for example the power in a circuit that has an EMF. Now we already know that P is equal to IV, and since the EMF has the same dimensions as the voltage, in that case the power due to an EMF can just be substituted as the following. Okay, this is the power of an EMF device. Okay, so the next thing that we will cover is we are going to move on to multi-loop circuits. And by multi-loop I mean that when the circuit is connected in parallel, right? So in that case, let's consider the circuit. Let me draw that down first. So let's say I have a circuit over here which has a resistor in this way, and it is also connected in parallel with another loop that has other components connected as so. Okay, now let's consider that this is EMF 1 for the first battery, and you see the direction of the current will be in this direction because of the positive and negative ends. And let's say this is EMF 2, and the direction of the EMF will be in this direction because of the direction of the current. So whatever current that comes out of zeta 1, which is EMF 1, will be in this direction. So let's call that I1, and this will be in I2, right, that comes from this direction. But for conventional reasons, I'm going to first define I1, because you understand, because we have two loops, the current will be divided, and in that case you will have contributions of I1 over here as well, right? So before that I want to just make sure I divide I1 first. Okay, so I'm going to consider that this current actually flows in this direction, we denote this as I3, which is the current that flows through resistor 3, and this is the current I1 that flows through R1, and this is the resistor R2. And if I consider I3 to be traveling from this direction, then I understand that I1 and I3 meet over here, and therefore there creates a loop where I2 should be in this direction, right? So this is the overall junction computation that I have. Now, as I know that current is conserved, meaning from a particular junction, whatever current goes in is the current that goes out. So in that case, I can write an expression for the currents that from this particular junction, you have I1 to enter and I3 to enter. So therefore, I1 plus I3, and I2 goes out. So therefore, it must be equal to I2. So for now, basically, the directions of the current are just arbitrarily given, right? So you can take any direction of the current you want arbitrarily. Just make sure that this equation holds, in the sense that you have incoming currents equal to the outgoing currents as such. Okay, so now for this I can make a junction rule which basically states that the sum of the currents entering any junction must be equal to the sum of currents leaving the junction. Now, this is often called as Kirchoff's junction rule or Kirchoff's current law. This is like an analog, actually not an analog, but an extension of Kirchoff's voltage law. Okay. Now, moving on, we see in the circuit that we have two loops, right? So in order for us to have an understanding of how the EMFs are working essentially, or basically how the potentials are changing from one point to the other, like we did for the single loop circuit, for this we need to consider two loops, right? One loop can be considered if we consider the left hand loop over here in a counterclockwise direction, meaning in this direction, and if we use also the right hand loop in a counterclockwise direction, is this in this direction. And it is easier if we can denote points that we are considering, যেহেতু ট্রাভার্স করতেছি কোন পয়েন্ট থেকে কোন পয়েন্টে যাচ্ছি সার্কিটে, সেটা ডিনোট করতে পারলে easier. So let's say we consider that this is point A, this junction over here, this is point B, and let's say this is point C and this is point D. Okay, so in that case, if we traverse the left hand loop in the counterclockwise direction, this one over here, from point B to just traversing it back to point B over here, so in that case the EMF contributions that we will encounter will be first zeta 1, right? Because I'm going in this direction, which is in the direction of zeta 1, so positive. And then I come to point A, and then I come over here where I encounter the component of the resistor, which is R1. So the current flowing through the resistor is I1, so therefore this will be minus I1 R1, because we are in the direction of the current, right? And the resistor essentially takes away from the potential. And then I move from point A to point D, and then I go back upwards, so I go towards point B again, but this one is in the opposite direction of I3, so therefore jeta minus har kotha chilo, I should get a plus, and therefore I guess I get plus I3 R3, and this should equal to 0 because I'm coming back to the same position, right? Now similarly for this loop, if we traverse the right hand loop in a counterclockwise direction now from point B, So I'm going counterclockwise from point B. So in that case, I will first encounter R3 over here, which is in the direction of the current. So in that case, I will get first minus I3 R3, right? And then I will encounter this resistor over here, which is R2. So in that case, since it is also in the direction of the current, I will get minus I2 R2, and then finally I will get zeta 2, but it will be in the opposite direction. So jeta plus or kotha chilo, I will get minus, and this will equal to 0. Now we have 3 equations at hand that we have to solve. We have to solve this one, which is for the right hand loop, and we also have this one, which gives us the relationship between the currents, right? So we have 3 of these equations that we have to solve, and we have 3 unknown currents, and hence they can be simultaneously solved if we want to solve them. So in that case, we can solve them simultaneously, and we would get the values of the currents respectively. Okay, now next what we need to do is we need to figure out how 3 resistances, if we have, let's say, a simple configuration like this one, where we have 3 resistors, right, which contribute 3 resistances to the circuit. If they are indeed connected in parallel, as you can see from here, how would their equivalent resistances be computed? Because that is what we did for a series circuit, right? So parallel jonno to equivalence resistance thakbe, like for any components of the resistor, we can always rearrange it to have equal contribution from an equivalence resistor or an equivalent resistor per se, right? So in that case, let's say if I have any resistor or a bunch of resistors that are connected in parallel as such, right, I can of course rearrange it in such a way as though I am connecting one resistor with the equivalent resistance of all of the 3. So R1, R2, and R3, like this, right? So let me consider that I have an EMF over here which is going in this direction, which is in the direction of the current. So I will have some current flowing over here. Now if this is some junction A, now since there is a divider in the wires over here, so of course I know current I will get divided, right? And I will have only partial of the current flowing through this branch, and therefore the rest will flow through over here. And I know some of the current will now get divided and flow through this branch. Let's call that I2, and again rest of the current will flow. Now let me call this I3, which is the current that flows through R3. And since the rest of the current flows through over here, if I1 goes in the first branch, then this must be I2 plus I3, where I2 goes into this branch, and then we're just left with I3 over here, right? So of course I2 and I3 come and meet over here, and then we are connected by I1 from this junction, and therefore I comes back to the circuit, right? So this is how you can draw the circuit configuration. Okay, so in this case, if we want to derive an expression for the equivalent resistance, we first write the current in each equal resistances. So that means that I can write I1 as basically V by R1, right? Because we understand that the voltage is not actually shared. When we have a parallel circuit, it is actually the same for each branch, right? In that case, I1 is so. I2 can be written similarly as V by R2, and I3 can be written as V by R3. And I know for a fact that I is the current that goes in, right? So that should be the accumulation of all the currents, which is I1 plus I2 plus I3, right? So I can write this as V times 1 by R1 plus 1 by R2 plus 1 by R3, and hence normally we would have the total current to be equal to the total voltage and the total equivalent resistance. So in that case, if you compare these two equations, we can figure out that 1 by R equivalent is actually 1 by R1 plus 1 by R2 plus 1 by R3. Okay, so extending if we want to extend this result to the case of many resistances, n number of resistances in particular, in that case I can write 1 by R equivalent equals to the summation over all of the resistances in this way, right? So this is for n resistors in parallel. So now you see that the comparison between the resistor and the capacitance is actually pretty vivid, which means that you have almost the opposite relationship between resistors and capacitors, because when we have capacitors in series, we have them to be, inverse, something that looks like this. And when we have capacitors in parallel, we have linear equations, which is the one that we had for series when we have resistances. Now the relationship is flipped for resistors. Resistor যখন series এ থাকে, we have a linear relationship, R1 plus R2 plus R3, something like that. And when we have parallel resistors, it is inverse. Okay. So I will pause this video over here. Because we will do another video for RC circuits, and I figured that maybe parting these videos into small intervals is good for you, so that you can cover the syllabus easily.